right, we're going to graph radical functions. We're going to focus on square root and cube roots today. Okay? Focusing on square root and focusing on the cube roots. Why are we doing this? Well, yesterday we talked about square roots, how they're not a function because when you took your parabola and laid it on its side, it didn't pass the vertical line test, right? Yeah. To make it a function, though, because it can be a function, we're just not going to include the piece that went underneath it. So we're only going to include the top piece. So it stays in the positives. So it's kind of like a rainbow. Right? Has a pot of gold, shoots out. Look at that, it's beautiful. Okay? So the inverse of a quadratic is a square root. That's the first thing up there. That's the inverse of a quadratic function is square root. Let's go right here. The inverse of a quadratic is a square root. So what do you think the inverse of a cubic is going to be? A cube root. Magic. Yep. What we're going to do is we're going to graph the parent function, and then we're going to move it with transformations. Whether we're adding and subtracting inside the radical or outside the radical. Look kind of familiar? Like with our quadratics, inside the parentheses with the x or outside the parentheses. Moved it up, down, left, or right. We've done this before. We've done it before. Just because it's a new function doesn't mean we're going to do it differently. It just means the graph we're moving looks differently. So we're starting off with the square root, which is going to be a rainbow, right? I'll show you tables. You don't have to use tables every time. If you're a visual person, like moi, you can draw the parent function on the graph first, because that'll never change. And then take each of those points and move them up, down, left, right, however many that you need. Okay? Or if you like making the tables, you can make the tables. I can just tell you, though, that using tables, you don't always get beautiful numbers. Sometimes it's easier just to look at it and move it. Okay? So, parent function, y equals square root of x. The x's we're going to plug in, let's make them perfect squares. Let's use 0, 1, 4, and 9. Let's use an x of 0, 1, 4, and 9. I would love for cell phones and earbuds to be gone out of sight. And I put it away. Yep, just don't even have it in front of you. Put them away. When we plug these in, we get their perfect squares. Look at that. 0, 1, 2, 3. And we're only using the positives, right? Because we're not going to, the negatives would make it not a function. So we're going to stick with just our positive numbers. Let's go ahead and graph them to get what our rainbow is going to look like. 1, 1, 4, 2. All right. This is the parent function. All of my transformations, up, down, left, right, because we're not going to condense or expand today. We're just going to keep it simple, up, down, left, right. So that 0, 0, that vertex, our pot of gold to our rainbow, that'll get moved up, down, left, right. And then my next point will always be up 1 over 1. And then the point after that will always be up 1 over 3. The point after that will always be up 1 over 5. 1, 3, 5. Remember that graphing we did with parabolas? Yeah. Still works, it's just laying over. Okay? So move your vertex and go 1, 3, 5 again. You gotta remember our transformations though. This one, square root of x minus 2. Is that minus 2 inside or outside the radical? Outside. So which way is it gonna move? Down. Nope. Down 2. You were right. It's gonna go down 2. Outside of the radical, it's going to move up or down. Negative means down. So that means my pot of gold, which was at 0, 0, is now going to be at 0, negative 2. So it'll be 0, negative 2. All of my y's get dropped down 2 points. So if you're making a table, all of your y's get subtracted by 2. If you're not making a table, physically move these points down 2 units. I've had a lot of people actually graph the parent function each time and then do the transformation after it. And it helps a lot. If you gotta do it, do it. I don't care. So our rainbow looks like that. And this was a translation down 2. Questions? Do you remember now? The up, down, left, right stuff, maybe? The new part is we're doing the square root, but the up, down, left, right should be stuff you've done before. We've done it before. We did it last semester. So my next one is square root of x plus 1. So how's that going to move? Up 1. Yep. So my pot of gold is not at the vertex 0, 0 anymore. Now it's at the vertex of 0, positive 1. And then 1, 1 is now 1, 2. Right? 4, 2 is now 4, 3. It's all getting bumped up 1. So that all my y's get bumped up in the table and on the graph for our translation of up 1.
Are we using the same x's for all of them?
So we were using the first ones for all of them.
For the square roots, yep. So my x's, these first couple ones did not change because what we're adding or subtracting is not attached to the x yet. It's about to be attached to the x, so that's when it's going to be different. Mm-hmm. But yeah, up and down, your x's will not change. If I move it left and right, your y's don't change, right? But your x's will shift. We good?
Yes.
All right, so we know outside the radical up and down. So that means inside the radical has to be left and right. So which one is this? If I have x plus 4 inside of it, what's it going to do? It is the left. Yes. Underneath our radical, it's going to be the opposite. That happened with our parabolas too. Our quadratics. If we had an x plus 4 squared, that meant it went to the left 4. So this means the whole thing gets moved to the left 4 units. So that means my x's, they get moved to the left 4, so you're actually subtracting 4. It went the wrong way. There we go. And then it looks like that. So our y's didn't change. So since we're moving to the left 4, you actually subtract 4 from your x if you're doing your table. This is when doing your table can get confusing. Okay? So that if this is when the table is screwing with your brain, then stop doing the table. Just physically move your points. Okay? You know where they always start. And all you got to do is move your vertex. And then from there, 1, 3, 5. As long as you know where your vertex goes, you can do the rest of your graph. So this was a translation to the left. So what do you think the next one's going to be? To the right. So that means my y's stay the same, but we're now actually adding 1 to my x's. We're moving to the right. So my rainbow gets shifted that way to give us a translation to the right one. How are we feeling? Feel okay?
Yeah.
Okay. My goal is to get through notes, and you hopefully will get through homework before you go today. Your homework is graphing. Obviously, we're graphing with our notes. That's why you got a sheet of 6 blank graphs, so you can use that for your homework. You don't have to freehand it today, like some of you had to do yesterday. Okay, moving on. We're getting into the cube roots now. Because it's a cube root now instead of a square root, is the way it's moved going to be different? Like if I still subtract 2 on the outside, will it still go down? Yes, it's just a new function, but all of the movement rules are still there. It's gonna look different, okay? A cube root comes from an x cubed. Do we know what x cubed looks like? No? Okay. Back in my day, this might be a dated reference, they called it the John Travolta of like that. Have you ever seen Saturday Night Fever? He does the dance move, disco movie. No, from the 1970s. Yeah, no. Look it up. It's a good one. That's what a cube looks like. Okay, a cube looks like this. If you look at my little math dance poster, he's hitting his John Travolta. Okay. So if we're gonna take John Travolta and we're gonna reflect him over the y equals x, we can almost kind of picture in our head what it might look like. A little bit. Well, it's not a parabola. It's a squiggle. So I'm still going to have a squiggle, but it's going to be probably on its side somehow. So a squiggle sideways. Let's see. It's going to have some kind of wiggle going on, like this guy does.
Is there 2 wiggles? No.
Technically there is.
Okay.
Yeah. So let's look. Let's actually graph it and see what it looks like. Because we're doing a cube root, let's use x's that are cubes. So let's use 0, 1, 8. I threw in -8 and -1 because can we do negative cube roots? Yes, we can. So let's do it. There's no restrictions with cube roots, just those square roots. So plot those points and see what kind of picture we're going to get. Looks like we have a little bit of a wiggle laying on its side. All right, with this one, do you see any patterns going on? What do you notice?
Like, if you flip that, it would be, no, never mind.
Okay.
It's kind of mirrored.
I just can't explain it.
Okay, it's kind of mirrored. I like that. So he notices it's almost reflected, like from the vertex in the middle this time on 0, 0. We can go up one to the right one, or we could go down and left. That's the same. And then you could go up or down one again, and then what is it that time? 6, 7, right? So this pattern is going to be 1 and then 7 because it's cube root. But it's going to reflect. So you'll have a top piece and a bottom piece on both sides. Again, tables, use them if you like them. You don't like them, always graph the parent one first and then physically move your points over. But the vertex this time, our little pot of gold, is that piece in the middle where the curve happens. All right, so cube root of x minus 4, what's going to happen to the whole thing? All right, is it right or is it down? Why is it down? It's outside of my radical. Good. So all of my y's are going to be subtracted by 4. It's a translation down. So our wiggle will be towards the bottom. Wiggle, wiggle, wiggle. Don't you deny me my happiness, Langston. So again, translations don't change, just the way the graph looks. What's the next one going to do?
I'm just grabbing this wrong.
Wait, yeah.
I keep getting like triangles.
That's because it's on here.
My next one is under. Yep. So you'll see it typed different ways here. The type that we did not extend that line up top. So that's why there's parentheses. But there's not always parentheses. Sometimes, like in the book, it does get to extend the line. I guess they have fancier font than I do. So they get to keep it going. So parentheses show it's under the radical.
Oh.
So this one is going to be to the left. Yep. So to be moved to the left 2 means your x's actually are subtracted by 2, but your y's stay the same. Because negative 10 plus 2 equals negative 8. Square root of that is negative 2. Make sense? So it gets moved over. Now remember, when you graph on one half, there are symmetrical points on the top half as well. And then magic happens. So how do we feel about it?
Not bad.
Not bad? Okay. If you're feeling weird about cubics, my advice, remember what the parent function is and where it starts. Ready for your homework assignment?
Yeah.
/ classwork? If you get through all 6, I'll give you a stamp.
There's 6.
There's 6. Mm-hmm. There are 4 square roots and 2 cube roots. Okay? So here are the 6 you're going to do. The first 4 are square roots. My suggestion, go ahead and write somewhere, up, down, left, right, what are you doing with your points? 25 and 27 are cube roots. What else is happening in 27? There's 2 things. It's going down 7. It's also going to the left 2. So 27 has 2 things going on. It's going to go left and down. Because you have one thing happening under the radical and one thing happening outside the radical. Okay? So 7, 9, 11, and 13 should be the rainbow. 25, 27 should be the wiggle on its side. Tables not required. If you don't like the tables, don't do the tables. Okay?
You make up the number for the table, right?
No, always use these. These are your original tables. So do the transformation from here. So number 7, square root of x plus 1. Right? That means it moves up 1. All of your y's got added 1. So these stayed the same, but all of your y's are going to go up 1. So 1, 2, 3, 4. Does that make sense? And then 11, it's going to move to the right 3.
So we still
Which
use
means you're
those
actually going to add 3 to each of these.
So we're still using those numbers.
Yep.
That's the only thing.
Yes, this is where it starts.
Okay.
Yep, that's where it starts.